Dipanjan, you could take your time out to come and talk about attention models and transformers to the folks here at the masterclass. Your session is going to be also live streamed on YouTube, just so that you're aware of that. And I'm sure a lot of your folks are going to be following your talk on there too. I'll pass you over the controls so that you can take it from here, just so that you are aware. We've covered with them, obviously, basic manipulation of data, whether it's image, speech, or text on the first day. The second day, we covered multi-layered perceptrons. The third day, we covered convolutional neural nets. And this morning, we covered RNNs and LSTMs with them. So they're all set up for your session, I hope. Thank you.
Sounds great. Sounds great. Okay, I think I will get started. So let me put some presentation. Okay, so hi everyone, thanks a lot for joining in. So today I will be talking about attention models as well as concepts related to attention in the context of a model which has been using a lot of different aspects of attention, and that is a transformer model. And in terms of the agenda, so we'll be covering briefly aspects related to what is deep transfer learning for NLP, given that transformers have been, I would say, one of the newest innovations which have, you can say, cracked transfer learning in the context of natural language processing, because earlier it was all about transfer learning and pre-trained models for computer vision. But I think in the last 2 to 3 years, we have seen a lot of progress being made in the context of natural language processing. So that is where definitely transformers have, I would say, cracked transfer learning for NLP. And we are definitely on our way to seeing even bigger or even smaller and better models. And we'll also talk about different aspects of what are sequential models, what is attention, what was the need and the motivation of the transformer model itself, try to unbox the transformer architecture essentials and look into different types of transformer models. And then we'll briefly talk about some of the major models in each of the categories of transformer models, like there is auto-encoding transformers, auto-regressive transformers, sequence-to-sequence transformers. So we'll briefly cover a couple of models from each of them. And finally, we'll wrap up with one of the most popular models in the area of efficient transformers, which focuses on faster training, a lower memory footprint, and so on. So now in terms of deep transfer learning for NLP, I'm pretty sure all of you know what transfer learning is. So transfer learning is nothing but a paradigm where you try to build a model assuming you have sufficient data, and once you train the model, you try to reuse the knowledge learned from that model into a new task. And the way you reuse the knowledge from a prior trained model is that you leverage some of the layers of that model, you leverage some of the weights from that model, and you try to adapt it to your new problem, and then you try to solve that problem. Now, some of the ways of doing this is take out some layers, take out the weights of those layers and plug it in directly into the new problem to be solved in the new data set. The other way is take out those layers and weights and fine tune them, change those weights via backpropagation as you're training that model in the context of your own problem. So that is where in transfer learning, knowledge which is gained from solving a prior task is reused and adapted to solving a new problem. But without transfer learning, what happens is every problem is done in such a way that it is trained in isolation. So models, let's say solving a certain task is trained. Again, you have a new task, a new data set, a separate model is trained, and so on. So knowledge and prior information is not shared amongst problems. So that is basically your traditional machine learning or deep learning, where learning is done in isolation. So the whole point here is with transformers, we have been able to do a whole lot of transfer learning where you can take a pre-trained transformer model and adapt it to your own kind of problems. We'll look at some examples also shortly. And in terms of transfer learning for NLP, I think sequential transfer learning for NLP has seen pretty much the biggest success in the field of NLP. And that is where there are two major steps in sequential transfer learning for NLP. The first phase of sequential transfer learning is called the pre-training phase, where we don't focus on any specific task, like let's say classification or whatever, named entity recognition and so on. We focus on a very generic task, like where you take in a bunch of text data. Now, common things could be, let's say, news articles or the Wikipedia database itself, which has pages and pages of text. And you build what is called as a generic language model on top of that text, which means you feed in entire words and sentences into this model, and the task at hand in the pre-training phase is predict the next word given you have processed a sequence of previous words, and also sometimes predict the next sentence given you have passed in the previous sentence. So this is where in the pre-training phase, the focus is to build a language model, a generic language model with the key or sole purpose of trying to learn the representation amongst different words, different sentences, and so on, so that the model can learn the right representations in the form of the relevant embeddings, which are generated for each and every word, consequently for sentences and paragraphs, and also hidden state embeddings inside each and every layer of the relevant models. So that is the key focus in the pre-training phase: build a language model, learn contextual representations or learn generic representations from different words and sentences. And there are, again, a variety of models which we have seen, starting from basic word embeddings, word to vec glove. We have also seen contextual embedding models like Elmo. We have also seen the newer transformer-based models also like GPT, BERT, and so on. Now, the idea is once you have built this kind of generic language model by ingesting a lot of text into any of these models, the next phase is probably the important phase for, let's say, practitioners like us, because that is where we try to take that pre-trained model and adapt it in the context of the real problem which we want to solve, right? Like, let's say sentiment analysis, or building a question answering system, or classification, regression. So this is where no matter what the type of problem we want to solve, we try to adapt that model in the context of that problem. And that is where we usually end up fine tuning the weights or the layers of these models, or plugging in these models with other downstream layers in our final model, and then fine tune the weights and the layers, train it in the context of our own problem. So usually when we are solving NLP problems, more than often we are focused on the adaptation stage. We don't really care much about the pre-training phase, but let's say in some cases, if you have like very custom data, or you have a decent amount of data, we have seen people pre-training models also, which can then be used. Like, let's say we have seen different variants of BERT come out, where people have trained or fine-tuned BERT in the context of financial documents. So we have FinBERT, we have BioBERT, we have CyBERT. So that is where people take pre-trained BERT models, and then they do some more pre-training where they ingest documents related to finance or related to scientific articles, and they build a more specific language model, and then you can adapt that model to solve problems, like, let's say, classifying scientific articles in different categories. So that is also there, but usually we focus on taking a out of the box pre-trained model and adapting it to our own problem. Coming to sequential models and attention, before we get into attention, there are a few concepts which you can recap, assuming you've already gone through them in a previous session. So one of the most important things is the embedding layer, which is, I think, uh, very, very critical when you're using any kind of deep learning models for natural language processing. So as you know, any kind of a deep learning model can only understand numbers. It can't understand text directly. And we need to process in sequential information in these models. So there is no notion of the classical NLP methods like you are doing a bag of words or TF-IDF and you count the number of times words are occurring. Okay, so here we are not dealing with count-based features. So the focus is more around sequential processing of words and sentences. So that is where, imagine you have a sentence with 3 words, just for simplicity sake. So let's say the sentence is movie was good. So what happens is, imagine there are more sentences like this. So the first task, which usually takes place in any kind of models like a deep learning model like a CNN or Lstm or even something more complex, is that you have a tokenizer which will process all these words and all these sentences, and it will find out all the unique words which are possible in our whole corpus of sentences or documents. And then it will create a mapping of a word to number mapping, as you can see here, and it will tokenize and process and generate sequences where it will encode every word into a number. Now, this number by itself doesn't have any meaning. All this number represents is what is the position of this word's embedding in the embedding layer. So the embedding layer is like a matrix where the number of rows of the matrix is equivalent to the number of words or unique words which are there in our corpus. And the number of columns of the embedding layer is the size of the embedding. Like, let's say if you have a vector of 128 numbers to represent each word, then the embedding size is 128. So this is where if movie is mapped to 2, that means the embedding or the word embedding for the word movie will be occupying 0, 1, 2, the second position here in the embedding layer. So consequently, what happens is when you pass in, let's say, a sequence of words for a document, movie was good, using the tokenizer mapping, it will convert it to numbers. Using these numbers, it will extract the relevant embeddings for each of these words. And then it will pass into the next layer, which could be an LSTM, which will basically process each of the words in the sequence. It could be a convolution neural network, which slides in convolution filters in one dimension across sequences of these word embeddings and extracts relevant features and so on. So that is where the embedding layer is very important because it helps in representation of words as embeddings. And something to remember is this embedding layer by default is trainable, which means the more you train the model and the more you learn from the mistakes your model makes via backpropagation, these weights are also updated. So over time, once the training is done, similar words will be having similar embeddings or be closer to each other in the context of the distributional hypothesis theory of word embeddings. Now, popular sequential models include convolution neural networks, where you can slide in filters of convolutions across the sequence of words in a one-dimension fashion. So CNNs are originally being used on image data, but you can also use it on text data. And then we have our classic deep learning models for processing sequential information. This includes recurrent neural networks, long short-term memory networks, which is a better variant of RNNs. You've probably learned about these. There is GRUs, which are faster than LSTMs. You have bidirectional models like bidirectional LSTMs or GRUs, which can process sequences of data in both directions. And You also have encoder decoder models, which processes a sequence of information and outputs a sequence of information like a language translation and so on. So just to recap for LSTMs typically can remember longer sequences of data than RNNs. And in the LSTM layer, you will have multiple LSTM cells where every cell will process one word. And the network usually takes in 3 inputs, where xt is the input of the current time step or the current word which gets processed here. ht minus 1 is the hidden state from the previous LSTM cell, which has processed the previous word in the sequence of words which you are processing. And ct minus 1 is the memory state of the cell state of the previous unit. And you have a bunch of gates here, as you can see, where this is the forget gate, which decides what information can be retained from the previous step. So if the sigmoid gets set to 0, it will forget what it has learned from, let's say, the prior hidden state here. If it's 1, it will allow the information to pass through also. So that is where the forget gate decides what is relevant to retain and what can be forgotten from the previous steps. We have the input gate here, which decides what information can be added in from the current time step. And the information which can be added from the current time step is usually represented in the form of a word embedding for each word. Like I said, everything always starts at the embedding layer itself. And then the output gate here decides what information finally is combined together from the previous cell state, the current word embedding from the new word in the current time step, the hidden state and the prior hidden state to finally form the final hidden state. So that is where this is the output gate, which decides what the next hidden state should be. In terms of LSTMs versus GRUs, I'm pretty sure you're already aware about it, but just as a recap, GRUs use only a reset gate and an update gate. So due to having less number of gates, what ends up happening is that the GRU models are usually faster than LSTMs, and often they can give a pretty comparable performance to LSTMs and can also sometimes be better than LSTMs. Though there is no guarantee that it'll always be better, but in many cases it is. Now, the next aspect is around bidirectional models, where bidirectional LSTMs are nothing special. It is like if you have one bidirectional LSTM layer, it just consists of 2 LSTM layers inside that one bidirectional LSTM layer. And what happens is you have 2 LSTM layers, as you can see here. Let's say you have one LSTM layer with the purple cells here. You have one LSTM layer with the green cells here, and this consists of one bidirectional LSTM layer. So for one of the LSTM layers, let's say the purple one, the input sequence of words are fed in forward fashion, which means from the start of the sequence of words to the end of the sequence of words, they are fed in forward fashion, each and every word, and it learns the relevant representations. Similarly, the other LSTM layer, let's say the green one, it processes a sequence of words in a reverse fashion, which means from the end of the sequence to the beginning of the sequence of words, as you can see, in a reverse fashion, and it learns its own hidden state representations. So what happens in bidirectional LSTM is these two are trained independently, but we end up combining the hidden state representations of the relevant LSTM cells at each time step for both the LSTM layers. So that is where the outputs of the 2 LSTM networks are concatenated at each time step. And then you leverage the concatenated hidden state representations to do some task, like you could pass it through attention models, you could pass it through some dense layers in terms of doing some classification and so on. And the whole point of doing this is sometimes the future words or sequences of words can help in encoding information and giving more context to words which are present prior in the sequence. Like in this case, if you see, he said teddy bears are on sale. Uh, the word teddy probably is pointing to a toy, but here he said Teddy Roosevelt was a great president. So the words like president are having a prior information that the word Teddy is not a toy but a person. So words later in the sequence can give more contextual representation to words prior in the sequence. And that is where preserving information from both past and future helps in understanding the context better. And the context is represented in these hidden state embeddings. So that is where bidirectional LSTMs have been very useful for different kinds of tasks, especially things like building custom NER models and so on. And there are various ways to use these models where you typically have an embedding layer. You will have your words and you will extract the relevant word embeddings. You'll plug it into a bunch of bidirectional LSTM or GRU layers. You can even feed in some pre-trained embedding models like a pre-trained fasttext model. And then we try to combine the hidden state representations of each LSTM cell and plug it into an artificial neural network to determine the importances of each of the hidden states, which we then pass as a flat vector into the final dense layers and the output layers. So that is where the new concept came of using what is called as a global attention layer, which tries to attend to or give importance to specific words in the sequence, which are very influential in predicting the outcome which you're focusing on. So that is where the global attention layer is probably one of the earlier, you can say, focuses into modeling attention for sequential models. Now, before we get into the attention model, something to just keep in mind is that sequential models usually have a layer, like let's say an Lstm layer, and you process in words at each sequence. You generate a hidden state embedding at each sequence, and the prior hidden state embedding goes as an input to the next Lstm cell, goes to the next, and so on. And you have all these hidden state embeddings. Now, in our code, like let's say using TensorFlow, Keras, and so on, if we set the return sequence as parameter of any of these layers, like an LSTM layer, to false, what usually happens is we don't get back all the intermediate hidden state representations. We only get back the hidden state representation from the final LSTM cell. And we plug this into our dense layers and so on. And by the way, this hidden state is nothing but it is just embedding, or it is just a flat vector of numbers. So we usually plug this into some dense layers, and then we do the necessary things like classification or sequence modeling and so on. So the hope is that all the prior hidden states have passed in enough relevant information from the prior word embeddings into this final hidden state. But that is where the concept came that why not take in all the hidden states and plug all of these into a dense layer where you give relevant importance to each of these hidden states, and then you do some kind of a weighted sum and so on. So the whole idea here was not to just rely on the last hidden state, but all the hidden states and do some kind of a weighing scheme. So this is just like the GradCam concept in computer vision, in case you're aware about it. That is like an explainable AI technique where you try to give a weightage to each and every feature map, and then you combine it in a weighted average or a weighted sum fashion to find out which areas of the image might be lighting up in terms of neurons firing when you're trying to predict a certain class. So it's the same thing here. It's like which hidden states are very important to predicting the outcome, whatever you're trying to predict. And if some hidden states are very important, that means those corresponding words could also be important. So this is where we talk about the global attention mechanism, where the whole perspective is instead of using the output from the last hidden state in the last LSTM or GRU cell in the layer, in the relevant LSTM or GRU layer, why not send all the hidden states from each and every one of the LSTM cells in that layer into a learnable function. And that learnable function is called a global attention layer. In short, a global attention layer is nothing special. It is just an artificial neural network. So it is just an artificial neural network which tries to learn the representations from each of these hidden states and tries to figure out that based on the output I'm trying to predict, which of these hidden states could be more influential in predicting that output. Like, let's say if I'm doing sentiment analysis and we have words not and good here, probably the hidden state representations of those two words are very influential in predicting the outcome. So it tries to learn those representations and assigns a importance score to each of these hidden states. Like, let's say the score here would be 0.6 and 0. Let's say 2. So combine it becomes 0.8 and the remaining would get, let's say, 0.1 and so on. So that is where the hidden state vectors or hidden state embeddings from the sequence of hidden states are fed into this learnable artificial neural network called as A of HT. And the objective of this artificial neural network is to produce a probability vector or a probability score vector of numbers, alpha t, where each alpha is basically a score or importance of the corresponding hidden state. So the final flat vector, which is passed into the corresponding dense layers in the future, is basically going to be a weighted average or a weighted sum, which is given by alpha THT, which could be like alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3 and so on. So you sum all of that up, and then you pass it as a context vector or a flat vector into the next dense layers and an output layer and so on. So the global attention layer can actually be um the global attention layer can actually be corresponded and condensed into two or three equations, which should now be very easy for you to understand. Where the first step of the global attention layer is that, hey, take in all the hidden state embeddings, pass it to the learnable artificial neural network. And by now, I think all of you know about what is an artificial neural network, so it doesn't require any introduction. An artificial neural network is just a bunch of neurons and layers with the sole task of multiplying the weights by the input features. So in this case, our input features or our x's are h1, h2, and so on. So WH, and then you add the bias. So this is a linear transformation. But artificial neural networks are all about nonlinear pattern extraction. So that is where you add in a nonlinear activation function tan h, and this gives you E of t. Okay, and this is done for each and every time step. And then the idea is to score the values of, or to score the importances of each of the hidden states. So that is where we take a softmax of E of t, which is nothing but squashing the raw values which come out as an output between 0 to 1. So these are like probability values or probability scores. So the way to do softmax is just e to the power of E of t by the sum of the exponents of all the e's. And once you do the alpha here, you end up getting a score for each of these hidden states. So the final flat vector which is passed is basically a summation of the products of alpha t ht. So alpha 1 h1 plus alpha 2 h2 and so on. They are all summed up and sent as a flat vector. So this is nothing but the global attention mechanism, which is followed in many models, including any kind of sequential models which you're using, like Lstms or bidirectional Lstms and so on. So just as a brief, and this is from Jay Alomar's blog, the references I'll link at the end of the session. So I definitely recommend checking it out. But the whole point here is you usually start off with a bunch of words which are processed by an LSTM cell for each and every word, as we discussed, to generate these hidden states. And each of these hidden states are a bunch of vectors, obviously, which it has learned over training across multiple epochs. You end up passing this to the learnable function. We discussed this, which is basically A of HT. and that gives you a raw score for each hidden state. This is known as E of HT, which we just covered, which is tan H of WX plus B. And then you squash this through a softmax function to produce alpha of T, where alpha of T is exponent of each of these scores divided by sum of the exponents. And you get a raw, not a raw, but a processed softmax score. Now you just do alpha of T into H of T, and you sum them up and you get up the context vector. So that is the main thing to keep in mind, that attention helps you in taking a weighted scheme of scores multiplied by the hidden states. And as you train the model across multiple epochs, you will end up having higher importances being attached to specific hidden states, which correspond to the relevant words in the sequence of words, which are very influential in affecting the outcome, which could be processing a next word in sequence. It could even be just a sentiment analysis problem where you're predicting the sentiment and so on. Now, coming to some slightly more complex models, one of the models which have been used in a lot of problems like language translation or named entity recognition is that given a sequence of words, in this case, let's say given a sequence of words in the source language, can I predict the sequence of words in the target language? So a classic language translation task. So the traditional model which is used here is known as an encoder-decoder model, which is a sequence-to-sequence model. And this is where we process in words from the sequence, which is the source language sequence. And like I said, every word will go into its corresponding RNN or LSTM cell. A hidden state is generated, and the hidden state of the prior LSTM cell is fed as an input to the next cell, and so on. So a traditional encoder-decoder model without attention will just take the last hidden state from the last LSTM or RNN cell on the encoder stack, and then it will pass it to the decoder stack to try and predict the word at each sequence, predict the word, compare with the actual word which is present, and learn from the mistakes via backpropagation. So the challenges with this kind of a scheme is that all the information which is learned in the intermediate hidden states are all compressed together to finally put it into one flat hidden state embedding coming out of the last LSTM cell, and then it's plugged into the decoder state. So a lot of information can be lost, especially if it's really longer sequences of data. Even though LSTMs can remember longer sequences, but it still has a lot of trouble to process those sequences and compress all the information in the last hidden state. So that is where the whole concept of attention came into play, that don't just take the last hidden state, take all the hidden states, take all the intermediate hidden states also. Pass it through a learnable function to learn the relevant weights, the alphas, and then take an averaged or a sum representation, a weighted sum representation, and then pass it to the decoder stage. So that is where the attention model gained a lot of favor in solving tasks like language translation and named entity recognition. So basically, sequence to sequence tasks, and gave a much superior performance. So just to sum up for encoder decoder models, each of the blocks, which means the encoder layer as well as the decoder layer, they consist of multiple RNN or LSTM cells. The hidden state embeddings are learned and updated at each time step as the new word flows in and the prior hidden state embedding also flows in. And the context vector, also known as the thought vector, is usually taken as the last hidden state embedding from the last LSTM cell and plugged in to the decoder if you're following the scheme of not using attention. But if you're using the attention mechanism, then you use a weighted sum of all the hidden states to create that final context vector or the thought vector instead of just using the last hidden state. So that is the process followed for standard encoder decoder models. Now we will this since now you have the context of the basics of attention, and now you also know what is a sequence to sequence model, where the encoder sequence processes in information from the input sequence of words, and the decoder sequence basically helps in outputting the sequence of words in the target context, which could be named entities, it could be a target language, and so on. So now let's discuss about what gave rise to the motivation that people thought that we should try and build better models, which gave rise to transformers. So there are many limitations and challenges with this encoder decoder scheme, or even like Lstms or GRUs in general. So the main thing which I mentioned earlier is that encoding a longer sequence without attention into a single context vector loses a lot of valuable information. So this is what I had mentioned earlier. If you only consider the last hidden state, if you are expecting a lot of information from each of the prior hidden states to be present and encoded into the last hidden state. But usually that becomes a challenge when you are processing really longer sequences of data. So that is where, if you don't use attention, that single context vector can end up in losing a lot of information from the prior hidden states. And researchers have also observed by doing multiple experiments that even with the attention scheme, it can become difficult and challenging to handle longer sequences and dependencies. It does become a challenge, and that has been proven through experiments. And the other challenge with these models is, and we discussed this, right, that to generate the next hidden state, you need the word embedding of the current word, and you also need the hidden state embedding from the prior LSTM or RNN cell, which means that you can't generate the new hidden state unless the previous word has been processed. So every word has to be processed in a sequence. Okay, that is the main thing to keep in mind. And this is where you can't parallelize the training. You have to train it sequentially, one word after another, and that can end up being very slow and time consuming. So sequential models have the limitations where they can't parallelize the training. It has to be sequential, one time step after another. So these were the main limitations or challenges which gave rise to people trying to build a better model, which gave rise to the transformer architecture. So now we'll talk about the transformer architecture model, and sorry, we'll talk about the architecture of the transformer model and try to dive into some of the essential concepts which should give you a good perspective of understanding these transformer models. So a lot of these visuals have been again taken from Jay Alamar's blog. I think personally knowing Jay, he's a great guy who tries to explain concepts through visual learning. So I would definitely recommend checking out his blog time and again to understand these things in a deeper context. But this session should give you enough to unbox the transformer model, where the whole point of a transformer model is that it is a layered and a stacked encoder decoder model. It is by nature a sequential model which processes in sequences of words. Now, the transformer model doesn't use the global attention layer, but it introduces some newer concepts of attention, and that includes self-attention, multi-headed attention, and encoder-decoder attention. So we'll talk about each of these as we go into the relevant blocks soon. And the best part about transformers is that it is not a sequential training mechanism as we saw in the RNN-based models or LSTMs. The training is completely parallelized, which means you don't need to pass in one word at a time in the sequence. You can pass all the words in one shot and it is processed and the hidden states are generated and so on. And as you may have already heard, transformers have achieved state-of-the-art performance on a variety of NLP tasks, pretty much beating the benchmark of each of those tasks. So unboxing the transformer model a bit more. At heart, a transformer model is a stacked encoder-decoder model. The usual architecture can include like 6 to 12 encoder layers or blocks. in each of these components of the encoder stack and the decoder stack. There are also really large versions of transformer models where you can even see like 24 encoder blocks or 24 decoder blocks. And we have even seen models like GPT-3, which use up to 96 blocks in the encoder layer. So imagine 96 decoder blocks. So some of these models are huge and very computationally expensive. Now, something to remember is not every type of transformer model uses both the encoder and the decoder stack. There are certain types of transformer models which use only the encoder stack. There are certain types of transformer models which use only the decoder stack, and there are certain types of transformer models which uses both types of stacks, which means it uses both the encoder as well as the decoder. Now, this is the visual from the original paper of the transformer model called Attention is All You Need. So I would recommend all of you to check out that research paper also whenever you get time. And this kind of shows you the major components of each of the encoder blocks and the decoder blocks. Okay, so this is representing one encoder block and this is representing one decoder block. So you can see that all the concepts we just talked about are all here, where you have multi-headed attention as well as self-attention here on the encoder side. You have the same aspects on the decoder side also. You also have a new concept called the masked multi-headed attention. We'll talk about this also on the decoder stack. You have some feed-forward neural network layers also, which help in adding some more nonlinearity into the modeling process. And you also have a concept which all of you might already be knowing from the aspect of residual networks like ResNet, which is there in computer vision, where you can see there are residual connections or skip connections from prior stages in the input going further into the next layers. So you can see there is a skip connection where the input word embedding is added with the output coming out from the attention layer. The output from the attention layer is added as an input also from the output going out of the feed forward dense layers. So the whole point of using these skip connections or residual connections is very straightforward. The residual connections help in propagating the raw input embeddings along with the intermediate outputs also to propagate them further through the network. And in that way, the prior input or prior representation signals can be passed into deeper parts of the network so that the signals don't get lost out completely because of additional processing. And also, if you consider in the reverse order for backpropagation, the gradients which are generated are flown further through the network, which means you can tackle problems like vanishing gradients and proper gradient flow happens through the whole network. So that is where transformer models have residual connections, just like models like ResNet. Now, unboxing these models a bit more, considering the encoder and the decoder blocks. So imagine you have 6 encoder blocks and 6 decoder blocks in the transformer model, and we are just looking at one of the blocks. So the encoder's inputs flow through a self-attention layer. The concept of self-attention is tricky, but we'll try to keep it intuitive. So the whole point of self-attention is every word attends or looks at every other word in the sequence of words which are being passed in. And every word tries to influence the embedding representation of every other word. So that means similar words will end up influencing each other's representations, and different words will not end up influencing each other's representations. And the outputs which come out from the self-attention layer are fed into a feed-forward neural network, which is just a bunch of dense layers. You have similar constructs also in the decoder stack, but between these two layers is another new layer called the encoder decoder attention layer. the whole point of the encoder decoder retention layer is to help the decoder focus on which parts of the input sequence are helping in influencing the output prediction generation. So that is where encoder decoder retention helps in giving relevant weights and importances to specific hidden state embeddings of words coming in from the input sequence. Now, only focusing on the encoder, that is our next step. So self-attention layer, and by the way, it is multi-headed self-attention. So imagine there are imagine there are 7 copies of this self-attention layer, and each of them do their own processing. So it's not just one self-attention layer, but 7 more copies of the self-attention layer, which are processing the words in the sequence. We'll talk about these copies and multi-headed attention soon. So just hold on to that thought. For now, imagine you have this one self-attention layer and you're processing in the input sequence of words. So the word embeddings are passed into the self-attention layer and they help in generating some hidden state embeddings. So in case of self-attention, as mentioned before, every word attends to or looks at every other word in this process, and every word tries to influence the embedding representations of every other word. The outputs coming in, the hidden state embeddings coming in from the self-attention layer, are fed into the feed-forward neural network layer, dense layers. The output coming in from these dense layers are fed into the next encoder layer and so on. Okay, so this process is followed for each and every subsequent encoder layer with the same workflow as the first encoder layer. Now, I mentioned to you before that when I am processing the words in the sequence of a transformer model, I'm not using LSTMs or something. It's using the self-attention concept. So it takes in the words in parallel all together and it helps in processing these in one shot. So it's not like first this is passed in and then this is passed in and so on. So if all the words are passed in one shot, then how does it know which word is before which word and so on? How does it capture that sequential information? So the whole point in transformer models was that um, you don't need to process additional layers of handling words in sequence one after other. The whole idea here is you process all the words in parallel, but add in some information to the word embeddings of each word so that the model can gauge from that additional signal that, okay, thinking is the first word, machines is the second word, and so on. So that is where the another innovative concept of these transformer models is encode that sequential representation as embeddings instead of adding additional layers or processing. So that is where for every word in the sequence, we have the raw word embedding, use some kind of a time scale function like a sine or cosine and generate another new embedding for every word, and that is known as the positional embedding of each word. Add in the two together and you end up with a word embedding with the time signal encoded inside the embedding itself. So the whole point here is don't use additional layers, but add in an embedding itself inside the raw word embedding, which will give the model enough signal that, okay, this is the first word, this is the second word, and so on. Okay, so the whole concept here is to add in this positional embedding into the word embedding to produce these as the inputs. Now, the question might arise, what does this positional embedding look like for different words in the sequence? So a positional encoding is nothing but a bunch of numbers. Again, it is just an embedding. Like in this case, imagine it's an embedding of size 4, though actual word embeddings are much larger. But the idea is that a bunch of numbers will help in making the machine understand which is coming first, second, and so on. Now, how are these embeddings generated? So that is where, if you look at the original transformer paper called Attention is All You Need, which I've mentioned before, it shows these bunch of equations which are or which are useful and very helpful in generating the positional time-based embeddings. Now imagine you have a sequence of 50 words. Okay, imagine you're processing a sentence of 50 words and they are represented in the y-axis. You can see there is like a pattern which is being generated. And this pattern is something which is generated by these equations. So imagine you have embeddings of size 512. Okay, so each embedding vector for every word, let's say for the 0th word, this is the positional embedding. For the first word, this is the positional embedding. Similarly, for the 50th word, let's say this is the positional embedding. Okay, so how does it learn, or how do we generate each of the numbers in the vector of 512 numbers, the embedding of 512 numbers for every word? How do we generate that positional vector or positional embedding? So that is where ordering of the words needs to be encoded into each of these embeddings. And these embeddings are called the positional encoding embeddings. Positional embeddings need to have the same dimensions as the word embeddings. So the size of the word embedding should also be 512 in this case. But the important thing to remember here is that we use a mathematical function to generate these positional embeddings. So plugging into this formula, POS denotes the position of the word or the token. So POS here ranges from 0 to 50, and I denotes the specific ith dimension of the positional embedding. So let's say I is 0, that means it is this number here, the first number of the 512th sized embedding vector. Similarly, if I is 2, then it will be, let's say here, the second number in the 512 dimensional positional vector. So I denotes the specific ith index or ith position in the positional embedding, I dimension or position. And the even positions, like let's say position 0, 2, 4, 6, 8, and so on in the positional embedding, it is generated from the sign function by plugging in this formula. And D of model, by the way, is the embedding size of the overall model. So that is where even embeddings are generated from the sign function, and odd embedding dimension values are generated by the cosine function. So if you plug in the relevant numbers into these equations, you end up getting these vectors, which are then added to the relevant word embeddings, and the embedding with time signals are generated. So that is how the sequential information is encoded into the sequence of words which are passed into the transformer layers. Now let's come back to self-attention. So the question might be that, okay, we have said every word attends to every other word. What is the self-attention? So in an intuitive way, self-attention is the whole concept of trying to see how other words can influence the meaning or representation of other specific words. So a simple sentence could be the bat was sleeping. Now, if you say the sentence, it immediately can come to your mind that what is this word bat? Is it a baseball bat or a cricket bat, or is it the animal bat itself? Now, you don't need to think about this. It automatically has probably registered in your brain that as soon as I said the bat was sleeping, you realize that it is the animal bat. And how do you know that? Because you already have a lot of contextual information which you've probably been learning since you have been a child, right? So you already know that non-living things can't sleep. It has to be a living organism. But how will the machine know it? The machine can't really know it, because the machine will only know based on the data you feed it. Machines by themselves are not intelligent. Artificial intelligence is something which is built based on data and models. So that is where self-attention is something which could help the model learn that by repeatedly seeing similar sentences, let's say from pages of Wikipedia, which are fed into the transformer model, it will understand that the word sleeping is very influential in affecting the meaning of the word bat. And it could help in associate bat with sleeping strongly and then give the indication that it could be an animal. And by the way, it is not like the model knows what an animal is, but when we talk about representations, it is all about the embedding representation because everything in NLP is represented by some kind of numeric representation. And in case of any deep learning model, as you already know, we started with the embedding layer, if you remember. So every word is represented as an embedding. So all the self-attention layer does is it helps in updating the embedding for the word bat. And the word sleeping is very influential in updating the embedding representation for bat. And consequently, the word bat is also influential in updating the embedding representation for the word sleeping. So that is where, again, it comes back to the distributional hypothesis concept of word embeddings, which started off with word2vec, which says a word is known by the company it keeps, and similar words will keep occurring in similar contexts. So self-attention basically helps in allowing the model to look at other positions in the input sequence for some kind of cues or clues, which can help in leading to a better encoding or embedding representation of each word. Okay, so that is what self-attention does. It does a bunch of tensor computations where embedding representations of other words could be very influential in updating and changing the embedding representation of specific words. And that is why it is known as every word attends to every other word and can change the embedding representation of each word. Now let's look at self-attention as a detailed overview as to what's happening behind the scenes in this self-attention concept. So usually what happens is we start off with a bunch of words in a sequence which is being processed. So in this case, we keep it simple, and let's say we have a sentence which is being processed, which has two words, thinking machines. So what is the first step which happens in the self-attention, or which happens in the self-attention layer, right? So the first step is even before that. So we have the word embedding, which we take in for every word from the embedding layer. So we have a word embedding for each word. We generate the positional embedding for each word, and we discussed it by using the sine and the cosine functions. We add in the positional embedding to the word embedding, and we generate a word embedding with a time signal for every word. Now, the next step is to generate vectors for queries, keys, and values. And how these vectors are generated is we multiply these word embeddings with weight matrices. And these weight matrices are for three matrices again, the query matrix, the key matrix, and the value matrix. And something to remember is it is just like embedding layers where these matrices are also having weights, which are updated and trained as you do backpropagation. So the query, key, and value matrices have weights which are learned over training via backpropagation. Each word's embedding vector is multiplied by these three matrices. So let's say we have the word machines. The vector for the word machines is multiplied by the query matrix to give the query vector. The matrix of the value, sorry, the matrix of the key vector is multiplied by the embedding vector of the second word here to generate the key vector and the value vector. And the same thing happens for each and every word. So every word's embedding vector is multiplied by these three matrices to generate the relevant query, key, and value vectors. So each word in the input sequence will end up having these three vectors. That is the first step. And these are known as projection vectors, and they usually have a smaller dimension than the word embedding dimension. So let's say if the word embedding dimension is 512, often we'll see that the query key and value vectors will be of size 64. Okay, so these are much smaller than the word embedding dimensions. And query key and value projection vectors are basically abstractions which help in computing the self-attention. And we'll talk about how the self-attention is computed shortly. So remember, first step, word embeddings generated, positional embeddings generated and added to the word embeddings. A word embedding with positional time signals are multiplied by the weights of the query matrix, key matrix, and value matrix to produce the query, key, and value vectors of every word. The next step after generating these query, key, and value matrices for every word is to compute what is called as the self-attention importance score with respect to every word. And how that is done is you compute the self-attention importance score by starting off with a reference word and then computing how important are the other words in the context of this word. So that is where we start off with a reference word. Say our reference word is thinking. And now we want to compute the self-attention score of every word in the context of thinking, including the word thinking itself. So that is where we compute a score for each word, considering a reference word. And the score depicts how influential all the other words might be in the context of this word, and in turn determining the embedding for the reference word, which is thinking. So how do we compute these scores? So this is where the query vector of the reference word, okay, so the query vector of the reference word, in this case Q1, is multiplied by the key vectors of each and every word. So Q1 times K1 gives you the raw self-attention score of thinking with respect to thinking. Q1 times K2 gives you the raw self-attention score of machines in the context of thinking. Similarly, you would do Q1, K3, and so on. Now, if you're doing vector multiplication, it is usually dot products to give you a number, a scalar. But if you are working with multiple words in a matrix notation, then you do a matrix multiplication. We'll talk about that. Here, just to keep things simple, we are showing you vector multiplication, but in reality, it is a bunch of matrix multiplication operations where, as I mentioned, all words are processed in parallel. Okay, so every processing is done in parallel. Here, we are just showing you step by step so you understand what's happening behind the scenes. So again, coming back to point, after getting the query key and value vectors for every word, next step is to generate these raw self-attention scores of every word in the context of a reference word. And this happens again and again for each and every word. Okay, so now let's say we have generated the self-attention score for thinking, for machines, and so on in the context of thinking. So after generating the raw self-attention scores, next step is to scale these raw self-attention scores. So that is where the raw self-attention score is divided by the square root of the embedding size of the query vector. And like I said, these projection vectors are of smaller dimensions. So in the base transformer model, these vectors have a size of 64 numbers. Okay, so the embedding size of these vectors is 64. And hence we take a square root of 64 and we divide it by 8. So we divide these raw scores, raw self-attention scores by square root of 64 and we get a scale score, okay? Now the question might come, why are we dividing by square root of 64? So this was the default value used in the original Transformers paper. They tried out different combinations and they saw that this score gave them the best possible performance. And it was said to have yielded more stable gradients. That's the reason they did this initial scaling. Okay, so once you have the scaled self-attention score for every word in the context of the reference word thinking, then you want to do a softmax, just like we did in the global attention layer, if you remember. So we pass these raw scores through a softmax function, which squashes the values between 0 to 1. And obviously, words which are very relevant and contextual to the reference word will have high softmax values. So obviously the word in the context of itself will always have a high softmax value, but we are also looking for other words which could influence this word. So let's say if we had this word, the bat was sleeping. So it could be that the word sleeping it will end up having a softmax score of, let's say, 0.7, which is very high in the context of the word bat. Okay, so those are the kind of things we want to capture. So every word ends up having a scaled and a softmaxed self-attention score in the context of the reference word again. So the next step will be to multiply these softmax scores with the value vectors. And that is what we do here. We multiply these value vectors of each and every one of the words with the scaled self-attention scores, okay? And the whole point of doing this, obviously, like I said, there are some words which will influence the encoding of each and every one of the words, right? So there are certain words like, let's say, bat and sleeping. So there are certain words like sleeping, which will influence the encoding representation of the word thinking. So that is where when you multiply those softmax scores with the value embeddings of all the words, there will be certain words which are not very influential in the context of the reference word. Again, remember, everything is happening in the context of this reference word. So there will be certain words which are not very influential in the context of the reference word. So multiplying by the scaled self-attention softmax score will help in kind of nullifying the effect of those vectors, right? The value vectors. So obviously, if a value vector has some numbers and the softmax score is, let's say, 0.001, essentially that vector has almost no influence in the final vector being generated. So that is where you multiply the softmax scores of every word with the corresponding value vectors. And then you take a sigma, you sum them up. So the value vectors are summed up to give the overall output vector, which comes as an output from the self-attention layer for each and every word. So this is where, if our reference word was thinking, all these scores are multiplied with the value vectors and summed up to give the hidden state representation of the word thinking, which comes out as an output from the self-attention layer. Similarly, the other step which will happen in parallel also is the word machines will have its own output from the self-attention layer, where the word machine will be considered as a reference word, and all these scores will again be computed, and then a vector will be represented here as the sum of all the softmax scores of softmax into value vectors, and then a sigma is taken considering machines as a reference and so on. So every word is considered as a reference word to generate the hidden state embedding as an output from the self-attention layer for that word. And all of this happens in parallel. So just to summarize, in self-attention, embeddings are generated for each word. A query key and value matrices or tensors are trained over the epochs. We multiply the query key and value tensors or matrices with the word embeddings to generate the query key and value vectors. Importance of each key is computed with respect to the query to get the scores. So query times key gives us the self-attention scores. Self-attention scores are divided by square root of the number of vector embedding dimensions of each of these query and key, which is 64. So square root of 64, we divide by 8 to generate the scaled self-attention scores. We softmax to normalize the self-attention scores. We take a product of the softmax times the value vectors and sum it up to produce the hidden state embeddings for each and every word, which is the output of the self-attention layer. And these self-attention layers, hidden state vectors or embeddings are passed into the feed-forward neural network as the next step. So just to, again, give some analogy here, query and key helps you in generating scores, and these scores are multiplied with the value vector to generate the final hidden state embedding per word. So a query is very analogous to the representation of the current word which we are using. Remember, always the current word is basically like the query word, right? A reference word. So it is like a reference word which we are using to score against all the other words using their keys. So this is where we care about what is the information which we are trying to search for. And that is where we have keys which are like labels for each and every word in the sequence of words against which we are trying to match a reference word. And the whole point here is once you multiply the query with the key, you end up getting, let's say, contextual words or responses which are very much related to your query. Okay. In that way, you find out contextual words which are very related to your query. And then what you get is you want to generate a final output representation for the reference word. So that is where you multiply these relevance scores with the value vectors of each of these words so that the more relevant words help in deciding the output representation of the reference word. Okay, so that is why query times key gives you relevance scores, and the relevance scores are scaled finally, and then relevance scores times values help you in getting an overall representation for the query word. And like I said before, everything happens in the form of tensors or matrix operations for the self-attention layer. So in reality, the words, let's say thinking machines is represented as a matrix of embeddings. Every word is not processed separately. Okay, everything happens in parallel. So the matrix of the word embeddings of all the words in the sequence are multiplied with the query key and value matrices to produce query key and value vectors, which are actually matrices because all the words are represented in sequence. And then when you multiply the query and the key vectors, you don't do it one by one. You do it in one shot using a matrix multiplication of query times key transpose. You scale it by 8. You take a softmax and then you multiply by the value vector matrix here for all the words in the sequence to generate the hidden state self-attention representations of each and every word. So it's all matrix multiplication operations. And now this figure from the original paper again, attention is all you need, will become very clear to you where query and key end up having a matrix multiplication operation. And this gives you like a self-attention layer output, which basically shows how important every word is in determining every other word's importance. And then what ends up happening is this is basically the output of this query times key transpose. You scale this by dividing by 8, take a softmax. And once that is done, you are at this stage typically. So now it's all about multiplying these scaled self-attention scores with the value vector. And that is exactly what is done here. So self-attention weights or scores are multiplied by the value vectors to give the final hidden state representations of each and every word, which is the output of the self-attention layer. Okay, so this basically shows the operations of the self-attention layer to generate the attention vectors of each and every word in the context of each and every word. That is self-attention. Now let's talk about multi-headed attention. So we just discussed about this happening to generate the attention hidden state embeddings for each and every word. But like I said before, this is not just self-attention, it is multi-headed self-attention. So what that means is you are not just doing this once. Imagine 7 other copies of this happening in parallel. So in reality, you're having 7 other copies of the hidden state self-attention vectors being generated. So a total of 8 of these are generated. Okay, so a total of 8 of these are generated. And this is done by basically, imagine you are having 7 other copies of this, but these are not exact copies. Like I said before, these weights are randomly initialized, right? So imagine you have 7 other copies of these matrices, but the weights are different from each other. So the whole point here is the final hidden state embeddings of the attention. Imagine each of them are slightly different from each other. Okay, so each of these outputs will be slightly different from each other. So this is where you have a total of 8 different versions of the query key and value matrices to generate 8 different versions of the query key and value vectors, and then generate the 8 different versions of the attention weights, and finally 8 different versions of the self-attention vectors. So that is where each of these self-attention matrices are overall consisted, like comprised into what is called as an attention head. So imagine you have 8 different self-attention heads. So imagine like this is a self-attention head. Okay, so all these operations, imagine, is a self-attention head. Now imagine you have 8 different versions of this. So 8 self-attention heads help you in getting 8 of these outputs. So for the input sentence, you get the word embeddings. You process these word embeddings by multiplying with 8 different versions of the query key and value matrices to generate 8 different versions of query key value vectors, which in turn generates 8 different versions of the self-attention embeddings, which are then combined and concatenated together to pass through the dense layers or the feed-forward neural networks. Okay, so now the question might come as to, we just talked about self-attention by computing this once. So now why are we trying to again replicate it 7 times? That is the question which might come to our minds, that why are we introducing this unnecessary additional complexity of 8 self-attention heads instead of having just one? Why are we having 8 of these? So the whole point of this inspiration is very much similar to what you do in convolution neural networks, if you remember from the days of computer vision. So the whole point in convolution neural networks is to generate different representations and different features of the same image. And that is why in a convolution layer, we usually set the number of filters to obviously more than one. Like we take 32 filters or whatever, 100 filters or 64 filters and so on. And the whole point is to try and extract different types of features from the image, like edges, corners, different patterns, textures, and so on. So we don't just use one filter there, we use multiple filters to extract different types of representations from the same one image. The same principle applies here. We want to understand different perspectives of the same word and the same sequence of words and the same sentence to be able to encode more and more diverse information from different perspectives of those same words. And that is the whole point of multi-headed self-attention. Try and encode different perspectives of those words. So if you look at this sentence, the animal didn't cross the street because it was too tired, and you look at the encoding representations of the 8 self-attention heads, see there are 8 colors here, so there are 8 self-attention heads, let's say for the 5th encoder layer. So if you look at the pre-trained model, which has already been trained, you can look that when we look at the word it and how its embedding representation was generated, you can see that the first attention head here, so 0, 1, 2, the first attention head here, the words animal is the words the and animal is very strongly influencing the encoding representation of the word it. And if you look at the second self-attention layer, the words tired is very much influencing, was tired is very much influencing the encoding representation of the word it. So what this means is the final, let's say, embedding representation for the word it, which is generated from this layer, is taking in some aspects from the word animal as well as the word tired. And that is very important, that you don't want things to happen in a linear fashion, but you want multiple words to ultimately affect the encoding representation of other words. That is the whole point of self-attention. So that is where, to bake in this representation from different perspectives, you end up keeping multiple self-attention heads instead of just one, just like filters in a convolution neural network. So that's the whole point of doing this 8 times. You want to encode different aspects and learn different perspectives of the same sentence. So let's talk about the remaining steps of the encoder block. So usually once your inputs are passed through the self-attention layer, you will get those self-attention based hidden state embeddings. Now we talked about the residual connection. So that is where you don't just pass in the hidden state embedding representations to the next layer, you add in the input embeddings also through the residual or skip connection, if you remember. So the input embeddings are also added with the self-attention embeddings as a part of the residual connections. And there are concepts like layer normalization, which is applied to speed up and stabilize training. And then you add in this input also to the output of the feed-forward network through the residual connection. So the residual connections here, 2 of them are here. They help in preventing issues like vanishing gradients across a huge network, as we discussed. And you have residual connections even on the decoder side, and the output from the encoder layer will go into each decoder layer. So the output from the topmost encoder layer will go as inputs to each and every one of the decoder layers. Now, once this is processed, we'll go into the next step, which is basically the decoder flow. So this is where the outputs of the top encoder is transformed into a set of attention vectors, which are the keys and the values. Just give me a second. I'll be back. Okay, sorry about that. So like I was saying, once you get the outputs from the last encoder layer, the representations from the last encoder layer go as inputs to each decoder layer. So again, just going back all these slides, so just hang on to this. If you remember the original representation of the encoder decoder stack, the output representations from the last encoder layer go as input to each and every one of the decoders, okay? So that is very important. Now coming back here, so how does the decoder flow happen here? This is where the encoding representations or the hidden state embeddings from the last encoder layer are transformed using the weight matrices into a set of attention vectors. So we have the key vectors and we have the value vectors. And these are passed into each and every decoder. And they are used by each and every decoder in the decoder stack by the encoder decoder attention layer. So you remember everything is very similar in the decoder as the encoder, where it uses the self-attention layer, where it uses the feed-forward neural network layers, but the only thing new was the encoder decoder attention layer. So that is where the encoder decoder attention layer leverages the key and the value vectors, which are transformed using the key value matrices by multiplying with the hidden state embeddings generated from the final encoder layer. And once that is done, it helps the decoder focus on appropriate places in the input sequence. So that is the whole point of it, that the keys and the value matrices are taken as an output from the encoder stack. it creates the query matrix from the layer below it. Okay, so the queries are basically created from the decoder layers below by using the query matrix. And it works just like multi-headed self-attention. And the whole point here is just like a sequence to sequence model, that the encoder decoder attention layer creates a layer of attention weights by, again, leveraging the key and the value with the query matrix to basically generate a sequence of weights which focus on specific parts of the input sequence, which are influential in predicting the next word in the sequence or predicting the sentiment and so on. And that is where the output of each step is fed to the bottom decoder. And the decoders bubble up all their decoding results, just like the encoders did. And then they make the final prediction. So this is where all the concepts are very similar in terms of embedding, adding in positional decoding sequences, because when you're predicting a word, you want to also compare with the actual reference word to see whether you're making the right prediction. Similarly, if you're predicting, let's say, a final label, you want to compare with the actual label and see whether you're making the right prediction, so that if there is a mistake, and there will be, you can do backpropagation and train the whole architecture. But one thing to remember is here we pass in everything in parallel, and we know the future words as well as the previous words. But if we are predicting words in sequence here, we are generating words in sequence, then you shouldn't be able to see the future words, right? Because these are words you're predicting. Okay, these are not input words you're processing. These are words you're predicting. So if you're trying to predict, I am a student or something, the future words shouldn't be generated, because then when the attention is being computed here with these query and values and the query matrix, then you will end up having the future words influence the importances of the previous words. So that shouldn't happen. So that is where, if you remember, I also mentioned, besides the encoder decoder layer, there is the whole concept of the masked self-attention layer. It's not just a pure self-attention layer. So that is where in the decoder, the self-attention layer is only allowed to attend to earlier positions in the output sequence. So let's say you're predicting the third word here. You will only be able to see the embedding representations of the previous two words. You won't be allowed to see the representations of the future words. And how it is done is by masking the future positions with minus infinity. So like I said before, there is no sequential processing in transformers. Everything is passed in parallel, but we mask the future positions of those words by putting a minus infinity. So everything is passed in parallel each and every time in the time step, but the future positions are masked with minus infinity, so that when I'm trying to predict the word I will only determine it based on the key and the value vectors coming in from the input sequence of words from the encoder side, and the query matrix which is being generated from the previous words in the sequence on the decoder side, but I will not be able to see the future words in the sequence. Okay, so this is a very important perspective of the decoder flow. Masked self-attention, okay? And then the final layers are pretty straightforward. It is just like any other deep learning model where you have built, where the final output representation from the decoder goes through a bunch of transforms where you get the logits, and then you call a softmax of the logits to generate the probability scores. You take the maximum probability score, take the argmax to get the position. And as I said, the tokenizer will have the word to number mapping. So you take the number, map it to the relevant word, and then you predict, okay, what is the next word I am trying to predict? Okay, so that is the final layers of the transformer model, going through the softmax transformation and predicting the next word in the sequence, let's say. So overall, this covers all the key concepts you need to know about the transform architecture. So hopefully a lot of these things make sense to you now in a more clearer way, in terms of a transformer is nothing but an encoder decoder stack. Encoder has a bunch of self-attention layers, which are actually multi-headed self-attention and feed-forward neural network layers. It also has residual connections. The output embeddings from the encoder layer are transformed into key and value vectors and matrices, which are then passed into each and every decoder layer in the decoder stack. Decoder stack uses encoder decoder attention to process the key and the value representations from the encoder along with the query representations coming in from the decoder side of the output sequence to be predicted to compute the attention scores. And it uses masked self-attention because we don't want to let future words in the output sequence help in predicting prior words in the sequence in the output sequence. So now let's talk about what you know, like more popularly, like what are the popular types of transformer models which are out there. So now we'll talk about transformer model architectures. So this is where we have auto-regressive models, auto-encoding models, sequence-to-sequence models. These are the three most popular type of transformer models. There are also multimodal models which are being researched more and more these days, where you can combine data of different modalities like text and images. So let's talk about these three types of models. So autoregressive models are models which use only the decoder stack of the transformer model. Like I said initially in the session, that not all transformer models use both the encoder and the decoder stack. So autoregressive models use only the decoder stack of the transformer model. Mask is used on top of the full sentence, so the attention heads can only see previous words. So this is where, since it is using only the decoder stack, it is using masked self-attention. Okay, that is something we just discussed, because we don't want to see next words to influence prediction of previous words. Decoder stack transformer models are trained or pre-trained. If you remember, in sequential transfer learning, there are two steps: pre-training and adaptation. So in the pre-training phase, the autoregressive models, which uses only the decoder, are pre-trained on the classic language modeling task. And this classic language modeling task is called guess the next token, also known as next word prediction. And all of you know about this language modeling task. You use it daily on your phones, where if you type in a bunch of words in the keypad of your phone, it suggests you the next word which you can select. Or if you type in a bunch of words in Google search, it shows you the next word or a next bunch of words which could be used. So the GPT family is a very popular family. All of you have, I'm pretty sure, heard about GPT-2 or GPT-3. So remember, GPT is a family of models, which is autoregressive transformers. GPT stands for generative pre-training. We'll come to that later. Now, auto-encoding models, as the name suggests, auto-encoding models correspond to the encoder stack of the original transformer model. They get access to full inputs without any mask. Okay, because here we are not like predicting the next word in a sequence usually, in terms of the key task at hand. So that is where they get access to the full inputs without any mask. But we do use a kind of mask when we are trying to build a language model, where we randomly mask out random input tokens to reconstruct the sentence and try to predict those random words. And those random words are masked out by corrupting them. And this is called the masked language modeling task. We'll come to that later. So remember, encoding, auto-encoding models uses only the encoder stack. The BERT family of models are auto-encoding models. And I'm pretty sure all of you have heard about BERT. So BERT stands for Bidirectional Encoder Representations from Transformers. It's a heavy name, but if you look at each word, you'll get the point. Bidirectional encoding representation from transformers, which means use the representations from the encoder stack. And we have sequence-to-sequence models, which are the true transformer models, which uses both the encoder and the decoder of the original transformer. Most popular applications include translation, summarization, question answering, and so on. All of these are sequential tasks where you process in a sequence of words and you generate a sequence of words. BART and T5 are probably the most popular models out there for sequence-to-sequence transformers. These are some popular transformer models. Nowadays, we also have GPT-3. Considering open source, GPT-2 BERT are very popular. Nowadays, you are getting newer models like GPT Neo, which is like people are trying to replicate GPT-3 in open source and so on. We'll discuss briefly about each of these transformers to an extent. We won't dive into too much detail because they are kind of very similar with minor variants. And again, the scope of the session is such that we can't go into like too much deep dive into each type of transformer because there are so many, it'll probably take forever. So coming to autoencoding transformers, our most popular autoencoding transformer is the BERT model, bidirectional encoder representations from transformers. In short, BERT is a trained transformer encoder stack. So it uses only the encoder stack in the transformer model. BERT base has 12 encoder layers in the model, and BERT large, like I said, some of the models will have even 24 layers or blocks. So BERT large has 24 encoder blocks in the model. So let's talk about sequential transfer learning in the context of BERT. So we just talked about sequential transfer learning, where there are two steps: the pre-training phase, which is more of a generic training phase, and then the adaptation phase, which is more of a specific training and fine-tuning phase. So in the pre-training phase, what happens is more of semi-supervised learning, where you take the BERT model with all its layers and you ingest large amounts of text data like Wikipedia, book corpus, and so on. And the whole idea is to predict the next word. But in case of BERT, since it's the encoder stack, we don't predict the next word, but we predict randomly masked words. So we are still doing language modeling, but it is called as masked language modeling because we remove random words from the sequence of words and we try to predict those. So the whole point here is to enhance the language processing capabilities of the BERT model by training on this generic task of understanding relationships between words and between sentences, and train those layers and the relevant embeddings so that in the future you can adapt this model to solve your own problems. So that is why the pre-training phase is all about trying to make BERT learn generic representations of different words and different sentences which are being passed into it, with the key task of predicting the next sentence. We'll come to that shortly, and also predicting missing words, which is masked language modeling. And once that adaptation step, once the pre-training phase is done, then we go into the adaptation step where we take in the pre-trained BERT model. So by the way, just to give you that notion, like if you're using the transformers library, which is very popular, or if you're downloading a pre-trained BERT model, like Google has already trained this task for you. You don't need to do this. So when you are using a BERT model, you are typically at this stage where you already have a pre-trained BERT model where the language modeling task has already been done. And then you have your own problem to solve, like let's say email spam classification. So here you will fine tune the BERT model in the context of your own problem. So you will adapt the BERT model in the context of your own problem, and that is known as the adaptation stage, where you take in a pre-trained BERT model, you pass in your own data, you add in your own relevant downstream layers like classification dense layers, and you adapt the BERT model in the context of your own problem, and you fine tune the layers and the weights. So that is where this model is then fine tuned to be able to do, let's say, email spam classification. So all of you as practitioners will usually focus on this step, but sometimes, like I said, if you want to do something very specific to your problem or maybe release something in open source for the community, you could do this step also. Like people have pre-trained language models on finance data, on scientific articles, and so on. And that is where you could also do this step, but usually we'll be focusing on the adaptation step. And usually in the pre-training phase, let's say Google is making a pre-trained model available for you. So what are the two main tasks of BERT's pre-training? So that is where, as we discussed, the first task is the masked language modeling task. where you have a sequence of words. We randomly delete some of the words in the sequence, and we don't delete it, but we mask it out by using a mask token. And we usually randomly mask around 15% of the tokens. And then we pass it through the BERT model, pass it through the softmax layers to try and predict these missing words. So we randomly mask out 15% of the words, and we try to predict them. So that is why it is known as a masked language modeling task, because we want to use the BERT model to predict the missing words, make relevant mistakes, and try to correct those mistakes and update all the layer weights and representations in the process. There is one more pre-training task which is done. It's not just masked language modeling in BERT. BERT also does this task of next sentence prediction, which is slightly supervised in nature, where the whole idea is BERT passes in one sequence of words between CLS and SCP tokens. It passes in the second sequence of words, and it tries to learn and predict, is sentence B entailing sentence A? So is sentence B supposed to be the next sentence after sentence A? Okay, so it tries to solve this problem also. So the whole point here is BERT is trying to learn representations amongst words as well as representation among sentences. These are the two main steps in the pre-training phase. In terms of tokenization, so BERT uses a word piece tokenizer, which is based on byte pair encodings. So BERT doesn't just tokenize based on spaces amongst the words. Okay, so that is something you should keep in mind. BERT uses a word piece tokenizer. So the word piece tokenizer segments words into subword level also if necessary, which means typically whenever you tokenize a sentence of words, it will introduce a CLS and SCP token, which is necessary for it to identify what is the starting and the ending of that sentence. And wherever there are rarer words, it will break those rarer and longer words into subwords. Like if you have a word walking, there could be other variants like walked, walker, walks, and so on. So it is usually segmented as walk, special token ing, or walk, special token ed. And notice that all of them will have walk in common. So that is where the whole point of doing this is, if you remember, in case of count-based models, you used to do stemming or lemmatization. Or whenever you use a fast text model, it has subword or character level n-grams, which are aggregated to get a word embedding. So that's the whole point of it, that the subwords will usually occur more frequently when training. So in that way, it can represent the subword level information in a more robust way because they will get more occurrences. And then to get back the embedding representation of the original word, you can just combine and average out the representations of the subwords. So that is where subword level information is very useful in case of BERT. It is essentially trying to bring in the same concepts of basically being able to represent words in a better way and generate better contextual word embeddings. And then there are other concepts also like pooled and token embedding. So we have the CLS token, which is just a standard identifier at the starting of the sentence. But as it goes through all the encoder layers, the final hidden state representation of the CLS token is considered as a representation of the overall sentence. So that is known as a pooled embedding. And the embedding representation of each and every word is known as the contextual token embedding or the contextual word embedding. So typically, a flat vector of size 768, which is the CLS token embedding, is the overall sentence representation, which you can get from the BERT model. Like this is the embedding layer of the BERT model. 768 is the embedding size, and 30,000 plus are the unique words in the corpus. So similarly, each and every 768 sized embedding is the embedding representation of the relevant tokens. And coming to point what you usually focus on is you take the pre-trained BERT model and you can adapt it to different tasks like sentence pair classification, sentiment analysis, named entity recognition, question answering, and so on. You can use it to solve a variety of tasks by fine-tuning it in the context of that problem. For text classification, we usually don't care about the next sentence prediction. So we don't care about the second sequence of words and SCP. All the words in a sentence or multiple sentences are plugged in between CLS and SCP tokens, and then they are plugged into the BERT model. The final CLS embedding sentence representation is extracted out from the topmost encoder layer, and that is plugged into our regular dense layers and the final output layer to softmax and give the prediction in terms of whatever classification we are doing, whether it's binary or multi-class. So just to recap, BERT uses the encoder stack in a transformer model, focuses on two main tasks in the pre-training phase: masked language modeling, next sentence prediction. It's usually optimized during training with different settings. You can check the paper of the BERT model. All of this is mentioned in more details, but it uses like the Adam optimizer, a low learning rate. It uses weight decay. It uses a one cycle learning rate where it spikes up the learning rate for initial steps and then it slowly decays the learning rate back to 1E6, 1E minus 6. And like I said, BERT is trained on Wikipedia and the book corpus. So total size is 16 gigs of data, which is pretty huge. And the base BERT model has a total of 12 attention heads, not 8 attention heads, and it has a total of 12 encoder blocks. And the hidden state embeddings are of size 768. And BERT base has a total of 110 million parameters, so it is a huge model. There are other variants which came out after BERT, right, where we have Roberta. Roberta stands for Robustly Optimized BERT Approach. Roberta doesn't focus on next sentence prediction, so its main task is masked language modeling. But it follows dynamic masking, not static masks like BERT, which means the masking pattern is randomly changed for every sequence fed to the model, versus BERT, where it is changed across every 10 epochs or so. Training and optimization settings are very similar to BERT, but Roberta is trained with larger mini-batch sizes and much higher learning rates. And you can see Roberta has been trained on a much larger data set, 160 gigs of data, which is not trivial. So it already includes book corpus and Wikipedia. It includes news data, web text, stories, and so on. Roberta based model is very similar to BERT. 12 encoder blocks, 12 self-attention heads per block, 768 sized hidden state embeddings, but the total parameters are slightly larger, around 125. Albert is one of the newer models which came out very recently. So it's like many companies built things like ExcelNet or Roberta and kept trying to beat BERT, and then Google came back again and released Albert recently, which again beat all the other models. Then again, more models keep coming out, as you all already know. So we already are seeing a lot of different types of transformer models coming out. So Albert is a very interesting model because it has been able to beat a lot of the previous models, but it is also very efficient. So Albert itself stands for a light BERT, and it leverages self-supervised learning to build out the language representations. The key focus of Albert is on more efficient model performance. And the way it does that is it says every hidden state embedding doesn't have to be of size 768. So the first optimization it does is factorization of embedding parameterization, which means the embedding matrix is separated between the input level embeddings, which are much smaller, of size of only 128, and the hidden layer embeddings are much higher, 768. So all the layers are not having similar embedding sizes of 768 as in Robert or BERT. Input level embeddings are much smaller. And also in any kind of these transformer models, the parameters are separate for each layer. Okay, but in case of Albert, the parameters are shared across all layers. And this helps in reducing obviously the number of parameters to be learned, as well as stabilizes the parameters. It focuses on two main tasks: mass language modeling, very similar to BERT, and sentence order prediction, where it's just like next sentence prediction, except for the negative samples, like the positive sample will be sentence A and B, but for the negative sample, the order of the sentences are reversed. Like it'll be B and A. It's not like if A and B are not in sequence, the label is 0. It's like B and A are reversed. So in that way, it focuses more on precision of ordering of sentences when it's predicting that. And the training optimization settings and data sets very similar. It uses book corpus, Wikipedia. The only difference is it uses the LAMB optimizer instead of Adam, and much larger learning rates and batch sizes similar to Roberta. And you can see that Albert base is very similar to BERT. It has 12 encoders, 12 self-attention heads, 768 sized hidden state embeddings, but 128 sized input state embeddings. And that's why the number of parameters are almost 1/10. So BERT base has 110 million and Roberta 125 million, but Albert has only 12 million parameters. So definitely a more efficient model in the transformers domain. So other models include autoregressive transformers, where the most popular autoregressive transformer is the GPT model. So GPT stands for generative pre-training. It is a stack decoder model. And you can see that GPT extra large has 48 decoder blocks. So these are like crazy models where people, or rather companies like OpenAI, have trained this on a huge amount of data. And given that this is just a decoder only model, it has been trained on the classic language modeling task of next word prediction. And as you can see that the GPT-2 model has been trained on a massive 40 gigabyte web text data set. So it's a huge model, basically, in short. It's not like it's a very small model. It probably has taken several GPU hours to train. And OpenAI was the company who initially didn't release this model. There was a lot of hype in terms of fake news generation, which it can actually do pretty well. But then finally the model architecture and the weights were all released. So GPT-2 autoregressive model built out of transformer decoder blocks. It's the classic language modeling task. Like I said, you type in some words in your keypad of your phone, it predicts the next word which you can use. So it's the same thing basically. Generates one token at a time given a sequence of words. And it's called autoregressive because it is self-generating, which means the generated tokens which are predicted by the model can be added back to the sequence of initial words, and then it keeps predicting the next word. So that's where this is the concept of autoregression. Generated tokens can be added back to the input sequence to continue generating further tokens. GPT-2 large has over 1.5 billion parameters. So you can imagine the scale of this model. It's a huge model with billions of parameters. So like even fine tuning it is a pain on even a high config system with, let's say, 16 or 32 gigs GPU memory. Now, GPT-2 uses only decoder blocks in its architecture. We just talked about that. And you know the decoder architecture. You have your feed-forward neural network layers, you have your self-attention, you have your encoder-decoder self-attention. Now, the main difference from the encoder-based models and the decoder-based autoregressive models is it uses only decoders. So it uses masked self-attention layer. It doesn't use a pure self-attention layer. And you know about the mask self-attention layer by now. We just discussed it a while back, where if you're predicting, let's say, this word, you can't see the words after this word because you don't want these words to influence predicting this word. So masked self-attention layer puts a mask and blocks information from tokens that are to the right of the position where a prediction is being computed. So if you're trying to predict the word orders, which is coming after a robot must obey, all the words after orders are masked out by setting minus infinity so that the attention weights and everything are masked out. So for all words passed as input to the model, GPT-2 will predict the next probable word and uses the same concepts of multi-headed attention, mass self-attention. The best part is since we are repeatedly using the same words along with some new words to predict the next word in the sequence, but the query key and value vectors of the already predicted words or already processed words can be reused. So in that way, some computation efficiencies have been done. And remember that the resultant vector from the self-attention layer is finally merged and concatenated because it's multi-headed. And then it is sent to a one-dimensional vector. Sorry, it's sent as a one-dimensional vector of size 768 for GPT-2 small and probably 1500 or so for the larger models. So the final flat vector of size 768 is sent to the feed-forward neural networks layers, the dense layers. And that is where it is passed to a two dense layer feed-forward neural network, where the first dense layer projects the 768 size self-attention embedding into a vector of size 3072. And then this 3072 sized vector is projected back into a size of 768 by the second layer in the feed-forward neural network, which uses a dense layer with 768 neurons. So the final output coming out from the dense layer, two dense layers in the feed-forward neural network, will be of size 768 again. Now you can fine-tune GPT-2 to do different tasks, like you can do language translation, just that you have to pass in an input sequence of words, pass in a special token, and then the output sequence of words. So given you fine-tune the GPT-2 model with enough such sequences, in the future, if you give it a sequence of words, and as soon as you pass the special token, it will start generating the output in the relevant language, like let's say French. You can even do summarization with GPT-2, where if you pass in the actual article tokens, a special symbol token summarize, and then the summary. So if you pass in historical data with the actual article and the summary tokens, in the future, if you pass in the actual article and as soon as you pass in the summary token, it will start generating the relevant summary. So in this way, you can fine tune the GPT model with some label data. Now let's talk about probably the most hyped model in the recent past from a transformers perspective. So that is where we have the GPT-3 model, one of the latest generative transformer models, which has been built by, again, OpenAI. It's a massive model because it has 96 stacked decoder layers, which I mentioned to you earlier. So imagine like this is much, much larger than what we have noticed in the GPT-2 model. It has 96 stacked decoder layers, and it has over 175 billion uh, model parameters, which is like huge. So over 175 billion model parameters, and each decoder block itself has 1.8 billion parameters. So it's like almost 100 times larger than the number of parameters of the GPT-2 model. So it's a crazy model with a huge number of parameters. And again, it has been trained as a language model to predict the next word. So the task remains the same, but the scale of the model is huge, as you have seen. And also the scale of the data is also large. As you can see that it has been trained on over 300 billion tokens, which is huge. GPU use of computation are 355 GPU years. So obviously they have used multiple GPUs, else it would take them forever. And you can see that the whole point here is you need to train this model on a large cluster of GPUs, and the whole cost here leads to $4.6 million. So you can imagine that this is really crazy. And that's why like GPT-3 has not been open sourced by OpenAI, because obviously they have spent a lot of dollars on this. So GPT-3 is available as a API which you can access. Now, GPT-3 can be fine-tuned with specific data samples to perform specific tasks. And this is where I think a lot of the hype has been created that GPT-3 can generate entire websites, it can translate text into code, and so on. So that is where the way it is fine-tuned is both the input and the outputs need to be present in the same sequence, which you pass into the model. Like, let's say if you're doing language translation, we just discussed it. You need to pass in the sequence like this: input sequence, special token, output sequence, and you need to fine tune the model in this way so that in the future, if you pass in this sequence, it will predict this. Okay, so in that way, you need to pass in the input and the outputs in the same sequence. Like for the code generation example, you would have example and then a sequence of words saying, okay, I want an input which says search. So I want a search bar. And then you have a two code symbol, and then you have, let's say, some JavaScript or HTML, which has the code to generate that search bar. So given you pass in enough such samples, if you pass in something new that, okay, generate for me a red button, and then the two code option, it will create a button class and generate the web page for you. So in that way, if you give enough sequences of data saying what you expect to be built, followed by a code snippet, then in the future, it should be able to build that kind of a representation for you. Again, it's not perfect, but given enough data, it should be able to do it. And that's why it's known as few shot learning. If you give it a few examples, it seems to adapt pretty well. The last type of model is sequence to sequence transformers. So this is where one of the most popular models include BART. So BART uses the full encoder decoder architecture, and it's a pure transformer model. BART is trained majorly with the following tasks of corrupting the text with an arbitrary noising function, as well as learning a model to reconstruct the original text. And BART, like I said, is a pure transformer model, which means it uses an encoder stack like BERT. It's an auto encoding stack, and it also uses a decoder stack. So it basically uses a stack of both the encoders and the decoders, trying to get the best of both worlds. And BART again leverages the same cross entropy loss and tries to predict the actual tokens and compute the loss and then backpropagate the gradients of the loss. And BART uses a variety of corruption schemes to try and make the model learn better representations. Like it includes things like token masking, deletion, rotation, infilling, permutation from the source sequence to try and predict those missing tokens in different ways. The other very popular model is T5, and T5 stands for text to text transfer transformer. Again, it uses a standard encoder decoder architecture very similar to BERT base. It is trained on a massive data set called the Colossal Cleaned Crawl Corpus, the C4 data set, which is almost 750 gigabytes. So you can imagine that some of these models have been trained on a huge amount of data. And T5 combines pre-training first and then fine-tuning for a variety of diverse NLP tasks. So basically, it is pre-trained on, again, the classic task of mass language modeling. It is called as unsupervised denoising training. So in the pre-training phase, what happens is different tokens are masked out, and then it's like, okay, this is the text, and these are the tokens which have been masked out. So can you predict, sorry, this is the original text. These are the tokens which have been masked out. So given this sequence, can you predict this output sequence, saying that, okay, this is the first token, this is the second token, and so on. So in this way, it is pre-trained on a variety of text, as we discussed, which is 750 gigabytes. And once the model is pre-trained, the best part is Google, who has built this model, has also fine-tuned this on a variety of tasks. So far we have seen that, okay, if we have a pre-trained BERT model, we have to fine-tune this model in the context of our own problems. Like you take a pre-trained BERT model, you fine-tune it for, let's say, sentiment analysis. Now you can't use that same model for, let's say, named entity recognition. You need to again take another copy of the pre-trained BERT model and fine-tune it for your own task of named entity recognition or language translation. But T5 is very innovative in that way, where Google has said that, why should we build separate models and fine-tune them separately on different tasks? Why can't we fine-tune the same pre-trained model on all the tasks together? So that is like a crazy concept, but it works in the way that it says that you can fine-tune on a wide variety of tasks by combining them using a similar format of data called the text-to-text format. And the text-to-text framework here suggests that you can use the same pre-trained model, the same loss function, the same hyperparameters on all types of NLP tasks, regardless of whether it's summarization, question answering, translation, classification, regression, whatever. But now the question might come to you that how is that possible? A regression is supposed to have a different loss function than classification, than translation, and so on. So the whole point here is it's just like we saw here. They are saying pass everything as input and output sequences, and that is known as the text-to-text format. You pass in a sequence of words, you pass in a special token, you pass the raw sentiment score, let's say. So the whole idea is, given the sequence, you make the model learn to generate the regression score. So there it's like same next word prediction, or like the final prediction. You give a sequence of tokens and you make it to do the summarization. You give a sequence of tokens, you make it predict the sentiment. You give a sequence of tokens, you make it predict the sequence of named entity tags. So that's the whole point of it. All you are doing still is predicting either a sequence of words or a sequence of one number or a sequence of one label. So everything can be formatted in this kind of data and can be passed into the same model. So in that way, you don't need different models to fine tune. And that is where for supervised fine tuning or adaptation tasks, the task name is usually mentioned at the beginning of the input. And then you have the input sequence, and then you have the output sequence. So in this case, translate English to German is at first. Then you have the input sequence. Then you may have a separator token, and then the output sequence in German. So if you give enough examples like this and fine tune the model, in the future, if you give it a sentence with tokens like translate English to German and then the sentence, you will get back the sequence in German. If you give a sequence of words saying summarize and then the article, it will summarize it for you and generate the summary. So that is where pass in everything as input output sequences in the same sequence to the model and fine tune it. And there it explored a variety of experiments to push the limits of transfer learning, and they found out that encoder decoder models outperformed decoder only models, fill in the blank style of denoising objectives, like mass language modeling worked best. Training on domain data is beneficial, and pre-training and then fine-tuning gives a much better performance in general. The last type of transformers we'll briefly discuss is efficient transformers. So we already discussed about models like Albert, which are very efficient. Now, why are we discussing about efficient transformers? So you just saw about all these models which are having a huge number of parameters, like BERT base is around 110 million parameters, base GPT 110 million, Roberta 125 million, BERT large is 340 million parameters. And you can see that the numbers keep increasing. And we don't have GPT-3 here, but that probably has beaten all the others where it has 175 billion parameters. So the cost associated with training these models is huge. The cost associated with fine-tuning these models is huge. And by cost, we mean everything, including GPU compute hours, the dollar value which you're spending probably per hour in the cloud, as well as the cost to the environment, which is, again, a critical issue where people are saying that running these models for hours is, again, not very beneficial for the environment and so on. Huge amount of power consumption, whatnot. But again, coming to point in terms of technical aspects, having a model with so many parameters is very difficult to maintain and tune and even deploy. So the whole point here was, can we achieve similar performance as these models, but remove some of the parameters which may not be influential? Or can we build a surrogate model which is much smaller than the original model, but tries to replicate the model performance of the original model? So that is where Hugging Face came up with DistilBERT, which gives almost up to 95% or more performance of the vanilla BERT model, but it has, as you can see, only 66 million parameters, so almost close to half or slightly more than half of the number of parameters of BERT. So DistilBERT, again, briefly uses a compression technique known as knowledge distillation. To be more specific, it uses teacher-student training principles, where we train the student model or the DistilBERT model to mimic the output distribution of the teacher model, which is the vanilla BERT model. And it is trained with the cross entropy on the soft targets, which means the probabilities from the teacher model, which means it is trained on the output, which is basically the output probabilities from the BERT model, not the actual hard output labels from the historical data. And it uses scale divergence to compare between the predicted and the actual output distributions, given that we are working with continuous probabilities. And DistilBERT has almost half the number of parameters from BERT and still retains 95% of the performance. Okay, so this gives you a variety of models, and this gives you the whole perspective of the different types of transformers. These are some research papers which are there in my GitHub. You can actually go anytime to my GitHub, and you'll probably find out the transformer NLP essentials repository, and you'll find a lot of these papers. And again, a lot of the blogs, which are pretty much from company blogs, Google, Facebook. Lstm's blog, I definitely recommend. It has a lot of interesting aspects and a lot of the visuals which you have seen today. So overall, this brings an end to the concepts. We'll go into some hands-on examples I'll probably show you in some Colab notebooks of how transformers can be used. But before that, just to wrap up the conceptual aspects, just remember that transformers are a stacked encoder-decoder model. It uses concepts like multi-headed self-attention, as well as encoder-decoder attention, and masked self-attention in case of the decoder blocks. And the encoder blocks feed in the information into the decoder blocks. There are models which use only the encoder stack, like BERT, Roberta, Albert, and so on. There are models who use only the decoder stack, like GPT family of models. And we have the pure transformer models like BART and T5. So overall, I think this should give you enough to start diving deeper into transformers. And for those of you who already know transformers, hopefully this is a nice refresher into the concepts you already know. So with that, let's go through some examples. in terms of how we can probably do transformers. So let me see if I can pull up some of those notebooks and I will show you. Just give me a moment. Let's see. Okay, so this is one of the first things I want to show you, that what is the power of transformer models in the context of diverse tasks in NLP. Like it could be classification, it could be named entity recognition, question answering, summarization, and so on. So we will look at all those tasks now. So here we are not doing any fine tuning. We are just showing you the transformers library, which has a pipeline construct. And you just need to plug in the task which you want to solve. And it will automatically load the best model for you, which is state of the art, and it will help you in making predictions directly. So this is where transformers are used directly in a pre-trained form. But you will see that the performance is quite good, even on new and novel tasks. And that is the whole point of these kind of models, where you can leverage pipelines to load a state-of-the-art model and start applying it on your data directly. And you can even specify a specific model name in case you don't want to load the default model. So let's dive right into it. In terms of, you need to install the transformers library. From the transformers package, you import the pipeline construct. And then you just say pipeline sentiment analysis. And as soon as you say this, you can see it is loading a pre-trained model with all the weights. So it does take some time. And once you have this, you have a ready state-of-the-art model, which has already been fine-tuned for sentiment analysis. So you can just start calling this model and pass in the text directly. Like, this is an excellent movie, really nice plot and casting. And you can see that the sentiment is positive because it is. The next one, you can see this movie was so not good. And you can see that the label is negative, which is pretty interesting. It is able to handle negation. I tried to like this book, but I definitely did not enjoy reading it. So it is able to gauge the facts of negation again. So this is where it's able to understand context, negation, and different aspects, and you didn't even need to code much. And this model pretty much outperforms any other standard unsupervised sentiment models like um, your text blob or Vader and so on, which you can typically look at from a unsupervised sentiment analysis perspective. The next one is named entity recognition. So you just need to load up NER inside the pipeline construct again. And once we do that, we can dive into doing named entity recognition. So that is where we just taken some text, can be any text. Here we have basically taken in text related to a news article about Facebook and some fake news or uh, data leakage issues which had happened. And then you just plug this into your NLP model, which has been a state-of-the-art transformer model for NER. And you can see all the entities get predicted, like Facebook is assigned to an organization, Mark Zuckerberg is assigned to a person, and then like Latvia location, Singapore location, London location, and so on. So out of the box, it starts performing pretty well. And then we have question answering. So you can load up a state-of-the-art question answering model by using the pipeline construct again. And this is where, let's say you have some database of text. This is from the World Health Organization on COVID-19. Okay, so this has been copied from the World Health Organization page. So this was just as a simple example to show that you can build a question answering let's say like a chatbot kind of a thing right out of the box with just a few lines of code where you load in the question answering model, you pass in your relevant database of information, and you can plug in questions like, okay, what's a coronavirus? And it tells you a large family of viruses which may cause illness in animals or humans. What is COVID-19? Infectious disease caused by the most recently discovered coronavirus, which is true because coronaviruses are nothing new. They have been there since ages, just that COVID is like a novel coronavirus, right? It's the newest one. What are COVID-19 symptoms? Fever, dry cough, tiredness. Pretty sure there are more, but in the context of this data, it's able to get it pretty well. How people get infected by touching objects or surfaces. How can we protect ourselves? Practicing hand and respiratory hygiene. I think that is pretty evident. So in that way, you can see that how you can use a state-of-the-art tuned question answering model and start using it directly out of the box. And then you have like fill in the blanks where you have a bunch of words and there is a blank. So you try to predict the next word, and it gives you a bunch of probable words which you can use from. You have summarization where here we have specified the specific model. So I'm using the BART model from Facebook. And again, I've passed in that bunch of coronavirus factual information from the World Health Organization website. And I just say, after creating the summarizer pipeline construct, that summarize this document. And then I just get the sentences and I join them together in one string. And you can see that this huge block of text, it has extracted the key information from this, and it's showing that COVID-19 is infectious disease caused by the most recently discovered coronavirus. It's now a pandemic affecting many countries globally. Most people recover without needing hospital treatment. Maybe 1 out of 5 can have difficulty breathing. So in that way, it shows you the key perspectives of this huge article and shows you the summary. So this is where I think we are heading more towards the area of being data driven rather than being more code driven, where because a lot of these models have been trained on a lot of data, you can fine tune it with some small amount of relevant data also, and it starts performing well. Doesn't mean it's a silver bullet. It can perform pretty poorly in a lot of tasks still, but we are definitely heading towards that domain now where we don't need to like sit and code everything from scratch, and we can focus on solving problems and become more like driven towards building better data sets which can help us reach to a better performing model. And then you have other things like translation pipelines where you can translate from a source language to a target language. You can use a GPT-2 model and text generation pipeline where you plug in this, it will load the pre-trained GPT-2 model. And you can pass in some text like the football game is about to, and it starts like writing complete conversations, as you can see, like as if someone is talking from the commentary box. So that's where like you can generate complete paragraphs of text. That's why GPT-2 had become infamous, where it can generate fake news. And of course, if you have a sentence, you can extract the relevant embeddings of every word and use them for further processing if you wanted to process it in your own way. So this shows you some of the possibilities of transformer-based models in terms of how you can start taking transformer models out of the box and start using them for your own purpose in terms of question answering, summarization, language translation, sentiment analysis, and so on. Okay, so now what we will do is I will try to plug in another notebook, which is all about fine tuning. So now you've already seen pre-trained transformers. So let's talk a bit about how you could probably fine tune transformers in the context of, let's say, sentiment analysis. Okay, so let's say you had your own data set and you want to fine tune these transformer models. So this is another tutorial where we'll talk about fine-tuning transformers. For this, you usually need a GPU. So all we do is we start with pip install transformers. We load some relevant dependencies like transformers, obviously. And now we'll load an open source data set, which is a benchmark data set available called the IMDb large movie review data set. And the whole point here is it has 50,000 movie reviews, where the review is the text here, and the sentiment is either positive, which is 1, or negative, which is 0. So the whole point is given the text, can we predict the sentiment? So now this is a very specific data set. So we need to fine tune BERT to be able to predict this. We can't use like a BERT model out of the box. So now let's try to simulate a small data set problem. Okay, so let's say we train on only 5,000 reviews, and then we want to test the performance on 40,000 reviews. So it's like the reverse of what you usually do in a train test split, where you do like a 70-30 split. Here I'm doing, let's say, like a 20-80 split, where I'm training on only 10 or 20% of the data, and I want to predict the performance on the remaining 80 or 90% of the data. Okay, and that's what the whole point of transfer learning is often, that if you have less data, can the model perform better by using a pre-trained model? So we will train our model on only 5,000 reviews. We'll validate the performance on another 5,000 data points, and we will test the performance on 40,000 reviews. So to keep things simple, we just take 5,000 reviews as our training, next 5,000 as validation, and the remaining 40,000 as our test. Now we do some basic text preprocessing, but we are doing this just because we want to train a baseline logistic regression model to show you that, okay, given that this is a benchmark data set, getting a performance of 80 or 85% is not that difficult, but the true performance gain then is, can we go beyond that? So we do text preprocessing for models like logistic regression, which is machine learning based. We usually don't need to do much preprocessing for BERT. So you will see that I will usually like pass the data directly to BERT. So this is where we do some basic text preprocessing, like removing HTML characters by using Beautiful Soup, normalizing the text data in terms of some removing the accented characters, and basic preprocessing, like remove HTML tags, remove any unnecessary new lines, lowercase the documents, remove any accented characters, fix the contractions, remove any special characters and spaces. No, not spaces, obviously. Remove any kind of special characters, which means we are keeping in the white spaces here. We are not removing the white spaces because we want to keep the spaces between the words. And then any kind of extra white spaces, we do remove it. So overall, we remove any extra white spaces. So any kind of extra white spaces which we have between words, like let's say there are 2 white spaces between words, we make them into like a single white space. And we remove any trailing and leading white spaces. And then we call this preprocess function on our training validation test. So now we train a simple logistic regression model. So for that, we use a count vectorizer to transform the text into a bag of words, which you must know about already, where every word becomes a feature, and we look at the number of times that word is occurring across each and every movie review. So we end up having 21,000 words as our features. So we train on 5,000 reviews, and we test the performance on 40,000 reviews. So once we transform the text into the numeric bag of words vectors, we train our logistic regression model, get the predictions on the test data, and check the performance. So you can see we reach a nice 85% performance. So even if we trained on 5,000 reviews, we were able to reach a 85% performance on the 40,000 reviews, because it's a benchmark data set. So it's a nice balanced data set also. Now the whole point is, can we go beyond this performance? This is like a baseline performance. So that's where the first model we'll apply is BERT. So for using BERT, we need to load the pre-trained BERT tokenizer because it contains the vocabulary which BERT was trained on. So we load the BERT tokenizer first. Now we need to prepare the data for BERT. Now BERT accepts three kinds of tokens. The first token is the word IDs, where every word is converted into a number, and that number occupies a position in the embedding layer. Words will also need to be masked or not masked, so that is where we need to add in the mask tokens and segment tokens. So why we need to add the segment tokens is, if you remember, BERT was originally trained on the task of next sentence prediction. So if I go to these slides quickly, BERT was originally trained on the task of next sentence prediction, where you had one sentence and then another sentence, and then you wanted to predict whether it was the first sentence or the next sentence or not. So that is where, because this task was trained, BERT was originally trained by using segment embeddings, where all the words belonging to the first sentence were assigned a segment embedding of 0, and all the words belonging to the second sentence were assigned a segment embedding of 1. But in our case, we don't care about this part during classification because we are not doing next sentence prediction. So that is why we will set all the segment embeddings to 0. So coming back to the tutorial, so mask and segment tokens needed to be added. So what we do is, we take in our document, which is basically the sentence of the movie review. We tokenize it using the BERT tokenizer. We assign a CLS and an SCP token to surround these bunch of tokens. And remember that whenever you are training any kind of classification model, your sequences need to be of equal length, which is why we do the padding or the truncation, if you remember. And why we need to do that is, otherwise we will not be able to train with a batch size of more than 1. Because if you're training with a batch size of 32, and let's say one sequence is 500 words and one sequence is 200 words, the model will give you a dimension mismatch error. So that is where, if you want to train in like a mini batch gradient descent mode, you have to do the padding and the truncation. So that is where we fix a max sequence length, which we take as an argument in this function. So let's say our max sequence length is 500, which means if we have movie reviews which are more than 500 tokens, we chop off all the tokens after 498 tokens, because we need to also put CLS and SCP. We convert the words into the numeric IDs, and we assign a mask of 1 for all those 500 tokens, let's say. Or if we had less than 500 tokens, like 200 tokens, so all those tokens will have a value of 1. Now, let's say we had a movie review of only 200 tokens, but the max sequence length is 500. So we need to pad it till 500, right? So you have already done padding in models like Lstm. So till the length reaches 500, pad it with zeros. So every word will have a position, every word will have like a position ID in terms of the embedding layer. As we discussed, remember, from the embedding layer, the word movie gets mapped into 2 and so on. So for padding tokens, we append 0. And for the mask also, for all the padding tokens, we append 0, which means whenever the model is processing any sequence, if the mask is 1, it knows that, okay, these are actual words. And if the mask is 0, it knows that, okay, these are padding words, so I don't need to pay attention to them. And as I said, the segment IDs will be 0 for all the 500 tokens. max sequence length, which in this case, if we choose 500, it will have 500 zeros. So in short, for any sentence which needs to be processed, you need to generate the word token IDs, you need to generate the mask IDs, you need to generate the segment IDs. And this is the data accepted by the BERT model. It will not accept any other kind of data. So let's say if the sentence was the movie was great, if you tokenize using this function, it will become CLS, the movie was great SCP. Let's say the max sequence length is 500. So this will get transformed into this three lists where the first list is the token IDs, where 101 is for CLS, 102 is for SCP. And let's say each of these words are mapped to some kind of a embedding layer row number, like 32 movie is 111, was is 10, great is 21. And the remaining tokens, still 500, are all zeros, padding tokens. Mask IDs will be one only for the words, rest are all zero. Segment IDs are all zero because we are not doing next sentence prediction. Okay, so this is the inputs which we will need to pass here using this. And we will load the pre-trained BERT model. We will add in our own dense classifier layers, and then we will fine tune this whole model. So that is where we set the max sequence length to 500. We tell that, okay, in our model, we will have 3 input layers because we want to pass in the input ID tensor. We want to pass in the masks. We want to pass in the segment IDs. So the input is basically a bunch of 3 vectors or 3 tensors. Inputs go into the pre-trained BERT model, which we load. So this is the pre-trained BERT model, which we are loading. And then we get the hidden state embedding representation, which is the pooled embedding. And you know what the pooled embedding is. We just discussed it. It is the embedding representation of the CLS token from the last encoder layer. So this is an embedding of size 768. We plug this into 2 dense layers. You have already used this if you have used TensorFlow Keras. So 2 dense layers with a standard dropout of 0.25. And this gets plugged into the final output layer with 1 neuron because we are predicting a 0 or a 1, a sigmoid activation function, create the model with the inputs and the outputs to plug in this whole network, compile it with the Atom optimizer. We fine tune using a low learning rate because we are fine tuning this model, and loss is binary cross entropy because we are doing binary classification. So this is what the model looks like. Takes in 3 sequences of 500 tokens, loads the BERT model, plugs in the last hidden state into, not the last hidden state, the CLS hidden state embedding into the dense layers and the output layer. And you can see the total number of parameters is close to 110 million, as we discussed for the base BERT model. So now we need to convert our, and you can see I'm using the train and the validation reviews directly. I'm not like doing any pre-processing really. So plugging in the BERT tokenizer, the train reviews, and max sequence length is 500 to generate the token IDs, the mask IDs, and the segment IDs for training and validation, and then just doing a model.fit on the training data, training labels, validation data, and validation labels, training for around 3 epochs. And you can see the batch size is 13. Why? Because the model is huge. If you try to train with a larger batch size, you'll usually get a GPU out of memory error on a standard 16 gigs GPU on Google Colab Pro. So once you fit this model, you can see that within the first epoch itself, validation accuracy has been 91%. And by the second epoch, it has almost reached convergence. And then we convert our test data into the token IDs, mask IDs, segment IDs again using a function. And then we just do a model.predict on the text on the test data. And you can see that the performance is a 92%, which is almost, not almost, it is like 7% more than what we observed in the base logistic regression model. So this does tell us that the transformer model is pretty powerful. And you can see that the code is not much. Like we built a model in less than 10 lines of code. Most of the work was in formatting the data in the right way. So this is where in just a couple of epochs, you're able to get a state-of-the-art performance on 40,000 reviews with training on 5,000 reviews. And then there is also the Distilbert model. In the interest of time, I'll keep this short, where for Distilbert, again, you need to load the Distilbert tokenizer. You need to do the processing again. The only difference between BERT and Distilbert is Distilbert was never trained on the task of next sentence prediction, so we don't even need to bother about the segment IDs. So all we need to care about is the token IDs and the mask IDs. We don't care about the segment IDs. So we all only care about the token IDs and the mask IDs. And the rest of the format is the same. Input layer consists of the input IDs and the mask IDs. Plug it into a pre-trained Distilbert model, which we load using Transformers TF Distilbert model from pre-trained. Extract the pooled output, which is basically the hidden state embedding of the CLS token. Plug it into the dense layers, the output layer, and everything else, the configuration is exactly the same. And then you can see that the number of parameters is around 66 million. So just like we discussed earlier, much lesser than the base BERT model. Then we again create the token IDs and the mask IDs for the training and validation data. We train it again for around 3 epochs, but now you can see I can pass a larger batch size because this is a much smaller model. So you can train with more number of examples per batch. And you can also see that when you were training the BERT model earlier, it was taking close to 435 seconds per epoch. So that is pretty huge. That's like almost 7+ minutes per epoch. And now if you see uh, in the Distilbert model, when you're training it, it is around 206 seconds per epoch. So the training time has effectively halved. So it's like 3+ minutes per epoch. And then you convert the test data into the token IDs and the mask IDs, and you predict on the test data, and you can see that the performance is 91%. So it's like it does live up to its expectation that the performance is almost 95% of the base BERT model, where we got 92% with BERT, we got 91% with Distilbert. So pretty good all-round performance. Okay, so that shows you how you can fine-tune a BERT model based on BERT and Distilbert model based on a standard classification problem. The next thing I will show is probably a more sequence to sequence problem. So that is where, let me see if I can pull this up. So now what we'll try to do is we'll try to show you how you can do a language translation model with transformers. That's pretty interesting. So the whole point here is we'll do a word level sequence to sequence transformer, which means now I will show you like a true transformer model, which uses both the encoder and the decoder stack. And we'll try to do a language translation system on a custom data set. So we'll try to fine tune a out of the box transformer model. So let's say we want to do a German to English translation. So all of you have used Google Translate, I'm sure. So if you go to Google search or you go to translate.google.com and you just select a source and a target language and you enter some words in the source language, it will show you the words in the target language. So this is where we will try to do the same. We'll try to build this kind of a language translation system. But again, given that we have a limited GPU infrastructure, we want to try and do what is possible in a short amount of time, obviously. So that is where the focus would be to load an open source data set, which is available in many things. Feel free to check out this site. And we'll build a sequence-to-sequence model where we'll process in an input sequence of words in German, and we'll try to predict the corresponding sentence in English. And as you all already know, a sequence-to-sequence model is also known as an encoder-decoder model, where the encoder processes in inputs using a sequence of words, and the decoder generates the output as a sequence of words which are compared against actual words, and loss is computed, and the backpropagation is done across all the layers. So for a sequence-to-sequence task, what we'll do is we'll keep things simple and use a wrapper library on top of the original transformers library. So this is the simple transformers library. It's a pretty popular library, which is open sourced. Definitely recommend to check it out. So what you need to do is you just need to do pip install simple transformers. Now we'll download the data set from the web and we'll unzip it. And then we'll load up the data. So as you can see, it has a bunch of English sentences and words and the corresponding words or sentences in German. Now, the challenge here is it has a lot of data. So what we are trying to do is we'll load only 10,000 sentences. So it's like effectively we'll train on around 8,000 sentences. So it shouldn't be that great a translation model because the data is very less. But we'll see regardless how well it works out. And the reason why we are choosing only 10,000 pairs is because we want the model to obviously complete training, and we also want to train it within the limits of the GPU infrastructure here. So now we just transform the data where we have a list of English sentences, and we have the corresponding German words and sentences for each of those English words and sentences. So we do some very basic pre-processing, like removing some symbols, and that's it, and lowercasing. Everything else is the same. We do some basic analysis, so we can see that these are not too long sentences. Like the maximum sequence length of English sentences is around 5 words, and maximum sequence length of the corresponding German sentences is around 9 words. And this is the distribution. So most English sentences have around 3 or 4 words, and most German sentences also have around 3 or 4 words. So now we do a basic train test split, and now comes the interesting part. So we will load the pre-trained Facebook BART model. We have already discussed about BART, if you remember. I'll briefly bring it up again just to set that context, where BART has an encoder and a decoder, and the whole point is, given a sequence of words, can it generate the output sequence? So we load the sequence-to-sequence module from simple transformers, and from that module we import the sequence-to-sequence model class and the sequence-to-sequence argument class, which will consist of all the configuration settings and training configuration settings for training a sequence-to-sequence model. And we set some basic logging to just show warning messages. Now we load up an object of the sequence-to-sequence args class, and it has different parameters. But again, like I said, we just want to keep the training short and simple. So we say that in the configuration settings, set the number of training epochs to 5 because we want to train for 5 epochs. Set the batch size to 16. Those are the two main parameters because, like I said, on a single GPU, you can't train with larger batch sizes. So that is very important. And there are some other parameters also, like evaluate the model as you're training it, and uh, show some verbose messages when you're training, and save it to the output directory in terms of the model and arguments and so on. And then we initialize the model, which means here we are loading a pre-trained transformer model. We haven't done any training yet. So sequence to sequence model class, we say that the encoder decoder type of model is BART, and the name of the model is the BART base model from Facebook. So we are saying basically that download the BART base model, which is available in Hugging Face's Transformers Hub. And when you want to train the model, please follow these model arguments to train and rather fine tune the model. And use CUDA means like use the GPU, obviously. So now what we do is we shape our data in the right way, saying that what is our input text, which is a sequence of words in German. We pass that as one column in our data frame, and the target text, so the corresponding words in English. So this is basically a data frame of the corresponding input and output sequences. And then we just train the model and also validate the performance here on the test data set, which is around 20%. And it does take a fair bit of time to train. And you can see we have set the configuration setting to verbose, so it shows all the outputs also in terms of the loss and so on, which does seem to go down. Okay, so the loss does seem to go down overall. Okay, and that is what matters. It's not just about the training loss, but the validation loss should also go down. So probably we could have trained it for more epochs, maybe to get a better performance. But again, we wanted to keep it simple. And then you can do different things, like you can evaluate the performance and check out the loss and so on. So once this is done, what we can do then is we can evaluate the performance and check the performance on some data. So the first thing we do is we see, okay, how is the trained model performing on the training data itself? So you can see here that some things it hasn't been able to learn anything, but in many cases it does make sense. Like, is Tom ill? It's predicting is Tom sick. So it has learned some representations that ill and sick are similar. So it's able to generate still decent sentences. It isn't mine, it's not mine, yours. So it's a hot day. He's my father, he's my dad. So it's pretty interesting that the model is able to learn some contextual representation. So it doesn't generate exactly as the target, but it's able to generate similar analogous responses. Okay. But in many cases, again, the performance is good, but in many cases it is not good, like dinner and lunch obviously are different. And in this case, it has completely well, it's kind of similar to the way that people are expressing their frustration, but it has told a completely different thing. So those issues are always there. Now, how does it perform on the test data? So on the test data, also we tried out. So you see that it is able to predict decently in many cases. And that's pretty interesting because obviously we didn't even show this data, and we only fine-tuned on 800 sequences, which were not even that long. And it does perform pretty decently if you see. So that is the power of these pre-trained transformer models in terms of being more data-driven and model-driven rather than focusing on um, building lines of code and sometimes customizing the logic and spending a lot of time in things like using specific word embeddings and then processing them, aggregating them, or passing them through some sequence of LSTM cells and so on. Here you can use a stacked encoder decoder model directly, focus more on getting the data, collecting more data maybe, and continuously improving these systems over time. So I think given the time at hand, that brings us to the close of today's session. Hopefully, this gives you a nice perspective on details of different types of transformers, as well as you have seen how transformers can be used on a variety of tasks, as well as how they can be fine-tuned for a simple label task like classification, as well as the sequence generation task like translation. So yeah, I think that is all from my side. I don't know if you have time for any questions, but yeah.
Thank you so much, Dipanjan sir, for taking the time out.
No problem. Thanks a lot. Yeah,
It was lovely having you here, and we would love to host you next time soon.
absolutely. Yeah. Feel free to reach out. And yeah, thanks a lot, everyone, for spending your weekend and attending this session. And I'm hoping all the future sessions are also very helpful for all of you. And yeah, have a great weekend, everyone.
You too, sir. And sir, we have one request.
Yeah.
Do you mind sharing these notebooks with us?
Yeah, you can go to my GitHub. So I can't share this notebook yet because this one is still being developed. I am doing a bunch of tutorials, so you can always check me out on LinkedIn. I will be actually releasing all of this step by step. It will take some time, so just give me
Sure.
some time. But if you just search for my name and go to my GitHub, I'll share this link also. You can get some of these links in transformer session, which I had done very recently also, and I will share this link. So you will get the text classification and also the other example. But do follow my space on LinkedIn if you get a chance. And again, you can just refer to my GitHub from time to time. I will soon bring up all the other notebooks also because I'm doing much more also like named entity recognition and other things. So hopefully I'm expecting those things will be up once I build like a series of articles and share them out. So yeah,
Right, sir. Thank you so much.
thanks a lot.